Chapter 41, Locality and the Fast File System. When the Unix operating system was first introduced, the Unix wizard himself, Ken Thompson, wrote the first file system. Let's call that the old Unix file system, and it was really simple. Basically, its data structures looked like this on the disk. S, inodes, data. The superblock S contained information about the entire file system. How big the volume is, how many inodes there are, a pointer to the head of a free list of blocks, and so forth. The inode region of the disk contained all the inodes for the file system. Finally, most of the disk was taken up by data blocks. The good thing about the old file system is that it was simple and supported the basic abstractions the file system was trying to deliver: files and the directory hierarchy. This easy-to-use system was a real step forward from the clumsy record-based storage systems of the past. And the directory hierarchy was a true advance over simpler one-level hierarchies provided by earlier systems. 41.1. The problem: poor performance. The problem: performance was terrible. As measured by Kurt McCusick and his colleagues at Berkeley, performance started off bad and only got worse over time, to the point where the file system was delivering only 2% of overall disk bandwidth. The main issue was that the old Unix file system treated the disk like it was a random access memory. Data was spread all over the place, without regard to the fact that the medium holding the data was a disk, and thus had real and expensive positioning costs. For example, the data blocks of a file were often very far away from its inode, thus inducing an expensive seek whenever one first read the inode and then the data blocks of a file, a pretty common operation. Worse, the file system would end up quite fragmented as the free space was not carefully managed. The free list would end up pointing to a bunch of blocks spread across the disk, and as files got allocated, they would simply take the next free block. The result was that a logically contiguous file would be accessed by going back and forth across the disk, thus reducing performance dramatically. For example, imagine the following data block region, which contains 4 files, A, B, C, and D, each of size 2 blocks: A1, A2, B1, B2, C1, C2, D1, D2. If B and D are deleted, the resulting layout is A1, A2, free space, C1, C2, free space. As you can see, the free space is fragmented into 2 chunks of 2 blocks instead of one nice contiguous chunk of 4. Let's say you now wish to allocate a file E of size 4 blocks: A1, A2, E1, E2, C1, C2, E3, E4. You can see what happens. E gets spread across the disk, and as a result, when accessing E, you don't get peak sequential performance from the disk. Rather, you first read E1 and E2, then seek, then read E3 and E4. This fragmentation problem happened all the time in the old Unix file system, and it hurt performance. A side note, this problem is exactly what disk defragmentation tools help with. They reorganize on-disk data to place files contiguously and make free space for one or a few contiguous regions, moving data around and then rewriting inodes and such to reflect the changes. One other problem: the original block size was too small, 512 bytes. Thus, transferring data from the disk was inherently inefficient. Smaller blocks were good because they minimized internal fragmentation, waste within the block, but bad for transfer, as each block might require a positioning overhead to reach it. Thus the problem. The crux: how to organize on-disk data to improve performance. How can we organize file system data structures so as to improve performance? What types of allocation policies do we need on top of those data structures? How do we make the file system disk-aware? 41.2. FFS. Disk awareness is the solution. A group at Berkeley decided to build a better, faster file system, which they cleverly called the Fast File System, FFS. The idea was to design the file system structures and allocation policies to be disk-aware and thus improve performance, which is exactly what they did. FFS thus ushered a new era of file system research by keeping the same interface to the file system The same APIs, including open, read, write, close, and other file system calls, but changing the internal implementation. The authors paved the path for new file system construction, work that continues today. Virtually all modern file systems adhere to the existing interface and thus preserve compatibility with applications, while changing their internals for performance, reliability, or other reasons. 41.3 Organizing Structure, the cylinder group. The first step was to change the on-disk structures. FFS divides the disk into a number of cylinder groups. A single cylinder is a set of tracks on different surfaces of a hard drive that are the same distance from the center of the drive. It is called a cylinder because of its clear resemblance to the so-called geometrical shape. FFS aggregates n consecutive cylinders into a group, and thus the entire disk can thus be viewed as a collection of cylinder groups. Here is a simple example showing the 4 outermost tracks of a drive with 6 platters and a cylinder group that consists of 3 cylinders. Note that modern drives do not export enough information for the file system to truly understand whether a particular cylinder is in use. As discussed previously, disks export a logical address space of blocks and hide details of their geometry from clients. Thus, modern file systems such as Linux ext2, ext3, and ext4 instead organize the drive into block groups, each of which is just a consecutive portion of the disk's address space. The picture below illustrates an example where every 8 blocks are organized into a different block group. Note that real groups would consist of many more blocks. Whether you call them cylinder groups or block groups, these groups are the central mechanism that FFS uses to improve performance. Critically, by placing 2 files within the same group, FFS can ensure that accessing one after the other will not result in long seeks across the disk. To use these groups to store files and directories, FFS needs to have the ability to place files and directories into a group and track all necessary information about them therein. To do so, FFS includes all the structures you might expect a file system to have within each group, e.g. space for inodes, data blocks, and some structures to track whether each of these are allocated or free. Here's a depiction of what FFS keeps within a single cylinder group. S, ID, DB, inodes, data. Let's now examine the components of this single cylinder group in more detail. FFS keeps a copy of the superblock S in each group for reliability reasons. The superblock is needed to mount the file system. By keeping multiple copies, if one copy becomes corrupt, you can still mount and access the file system by using a working replica. Within each group, FFS needs to track whether the inodes and data blocks of the group are allocated. A per-group inode bitmap, IB, and data bitmap, DB, serve this role for inodes and data blocks in each group. Bitmaps are an excellent way to manage free space in a file system because it is easy to find a large chunk of free space and allocate it to a file, perhaps avoiding some of the fragmentation problems of the free list in the old file system. Finally, the inode and data block regions are just like those in the previous very simple file system, VSFS. Most of each cylinder group, as usual, is comprised of data blocks. Aside, FFS file creation. As an example, think about what data structures must be updated when a file is created. Assume for this example that the user creates a new file /foo/bar.txt and that the file is 1 block long, 4 KB. The file is new and thus needs a new inode. Thus, both the inode bitmap and the newly allocated inode will be written to disk. The file also has data in it, and thus it must also be allocated. The data bitmap and a data block will thus eventually be written to disk. Hence, at least 4 writes to the current cylinder group will take place. Recall that these writes may be buffered in memory for a while before they take place. But this is not all. In particular, when creating a new file, you must also place the file in the file system hierarchy, i.e. the directory must be updated. Specifically, the parent directory foo must be updated to add the entry for bar.txt. This update may fit in an existing data block of foo or require a new block to be allocated, with associated data bitmap. The inode of foo must also be updated both to reflect the new length of the directory as well as to update time fields, such as last modified time. Overall, it is a lot of work just to create a new file. Perhaps next time you do so, you should be more thankful or at least surprised that it all works so well. 41.4 Policies: How to allocate files and directories. With this group structure in place, FFS now has to decide how to place files and directories and associated metadata on disk to improve performance. The basic mantra is simple: keep related stuff together. And its corollary: keep unrelated stuff far apart. Thus, to obey the mantra, FFS has to decide what is related and place it within the same block group. Conversely, unrelated items should be placed into different block groups. To achieve this end, FFS makes use of a few simple placement heuristics. The first is the placement of directories. FFS employs a simple approach: find the cylinder group with a low number of allocated directories to balance directories across groups and a high number of free inodes to subsequently be able to allocate a bunch of files and put the directory data and inode in that group. Of course, other heuristics could be used here, e.g. taking into account the number of free data blocks. For files, FFS does two things. First, it makes sure, in the general case, to allocate the data blocks of a file in the same group as its inode, thus preventing long seeks between inode and data, as in the old file system. Second, it places all files that are in the same directory in the cylinder group of the directory they are in. Thus, if a user creates 4 files, /a/b, /a/c, /a/d, and b/f, FFS would try and place the first 3 near one another, same group, and the 4th far away, in some other group. Let's look at an example of such an allocation. In the example, assume that there are only 10 inodes and 10 data blocks in each group, both unrealistically small numbers, and that the 3 directories, the root directory /a and /b, and 4 files /a/c, /a/d, /a/e, /b/f are placed within them per the FFS policies. Assume the regular files are each 2 blocks in size and that the directories have just a single block of data. For this figure, we use the obvious symbols for each file or directory, i.e. / for the root directory, A for /a, F for /b/f, and so forth. Note that the FFS policy does 2 positive things. The data blocks of each file are near each file's inode, and files in the same directory are near one another, namely /a/c, /a/d, and /a/e are all in group 1, and directory /b and its file /b/f are near one another in group 2. In contrast, let's now look at an inode allocation policy that simply spreads inodes across groups, trying to ensure that no group's inode table fills up quickly. The final allocation might thus look something like this. As you can see from the figure, while this policy does indeed keep file and directory data near its representative inode, files within a directory are arbitrarily spread around the disk, and thus name-based locality is not preserved. Access to files /a/c, /a/d, and /a/e now spans 3 groups instead of 1 as per the FFS approach. The FFS policy heuristics are not based on extensive studies of file system traffic or anything particularly nuanced. Rather, they are based on good old-fashioned common sense. Isn't that what CS stands for, after all? Files in a directory are often accessed together. Imagine compiling a bunch of files and linking them into a single executable. Because such namespace-based locality exists, FFS will often improve performance, making sure that seeks between related files are nice and short. 41.5 Measuring file locality. To understand better whether these heuristics make sense, let's analyze some traces of file system access and see if indeed there is namespace locality. For some reason, there doesn't seem to be a good study of this topic in the literature. Specifically, we'll use the SEER traces and analyze how far away file accesses were from one another in the directory tree. For example, if file F is opened and then reopened next in the trace, before any other files are opened, the distance between these 2 opens in the directory tree is 0, as they are the same file. If a file F in directory dir, i.e. dir/f, is opened and followed by an open of file G in the same directory, i.e. dir.g, the distance between the two file accesses is 1, as they share the same directory but are not the same file. Our distance metric, in other words, measures how far up on the directory tree you have to travel to find the common ancestor of two files. The closer they are in the tree, the lower the metric. Figure 41.1 shows the locality observed in the seer traces over all workstations in the seer cluster over the entirety of all traces. The graph plots the difference metric along the x-axis and shows the cumulative percentage of file opens that were of that difference along the y-axis. Specifically, for the seer traces marked trace in the graph, you can see that about 7% of file accesses were to the file that was opened previously, and that nearly 40% of file accesses were to either the same file or to one in the same directory, i.e., a difference of 0 or 1. Thus, the FFS locality assumption seems to make sense, at least for these traces. Interestingly, another 25% or so of file accesses were to files that had a distance of 2. This type of locality occurs when the user has structured a set of related directories in a multi-level fashion and consistently jumps between them. For example, if a user has a src directory and builds object files, .o files, into an obj directory, and both of these directories are subdirectories of a main proj directory, a common access pattern would be proj/src/foo.c followed by proj/obj/foo.o. The distance between these two accesses is 2, as proj is the common ancestor. FFS does not capture this type of locality in its policies, and thus more seeking will occur between such accesses. For comparison, the graph also shows locality for a random trace. The random trace was generated by selecting files from within an existing seer trace in random order and calculating the distance metric between these randomly ordered accesses. As you can see, there is less namespace locality in the random traces as expected. However, because eventually every file shares a common ancestor, e.g. the root, there is some locality, and thus random is useful as a comparison point. 41.6. The large file exception. In FFS, there is one important exception to the general policy of file placement, and it arises for large files. Without a different rule, a large file would entirely fill the block group as it is first placed within, and maybe others. Filling a block group in this manner is undesirable, as it prevents subsequent related files from being placed within this block group, and thus may hurt file access locality. Thus, for large files, FFS does the following. After some number of blocks are allocated into the first block group, e.g. 12 blocks, or the number of direct pointers available within an inode, FFS places the next large chunk of the file, e.g. those pointed to by the first indirect block, in another block group, perhaps chosen for its low utilization. Then, the next chunk of the file is placed in yet another different block group, and so on. Let's look at some diagrams to understand this policy better. Without the large file exception, a single large file would place all of its blocks into one part of the disk. We investigate a small example of a file, /a, with 30 blocks and an FFS configured with 10 inodes and 40 data blocks per group. Here's the depiction of FFS without the large file exception. As you can see in the picture, /a fills up most of the data blocks in group 0, whereas other groups remain empty. If some other files are now created in the root directory, there is not much room for their data in the group. With the large file exception, here set to 5 blocks in each chunk, FFS instead spreads the file spread across groups, and the resulting utilization within any one group is not too high. The astute reader, that's you, will note that spreading blocks of a file across the disk will hurt performance, particularly in the relatively common case of sequential file access, e.g. when a user or application reads chunks 0 through 29 in order. And you are right, oh astute reader of ours, but you can address this problem by choosing chunk size carefully. Specifically, if the chunk size is large enough, the file system will spend most of its time transferring data from disk and just a relatively little time seeking between chunks of the block. This process of reducing an overhead is called amortization and is a common technique in computer systems. Let's do an example. Assume that the average positioning time, i.e. seek and rotation for a disk, is 10 milliseconds. Assume further that the disk transfers data at 40 MB per second. If your goal was to spend half our time seeking between chunks and half our time transferring data, and thus achieve 50% of peak disk performance, you would thus need to spend 10 milliseconds transferring data for every 10 milliseconds positioning. So the question becomes, how big does a chunk have to be in order to spend 10 milliseconds in transfer? Easy, just use our old friend math, in particular the dimensional analysis mentioned in the chapter on disks. Multiply 40 MB per second times 1024 KB over 1 MB times 1 second over 1000 milliseconds times 10 milliseconds equals 409.6 KB. Basically, what this equation says is this. If you transfer data at 40 MB per second, you need to transfer only 409.6 KB every time you seek in order to spend half your time seeking and half your time transferring. Similarly, you can compute the size of the chunk you would need to achieve 90% of peak bandwidth. Turns out it is about 3.6 MB, or even 99% of peak bandwidth, 39.6 MB. As you can see, the closer you want to get to peak, the bigger these chunks get. See figure 41.2 for a plot of these values. FFS did not use this type of calculation in order to spread large files across groups, however. Instead, it took a simple approach based on the structure of the inode itself. The first 12 direct blocks were placed in the same group as the inode. Each subsequent indirect block and all the blocks it pointed to was placed in a different group. With a block size of 4 KB and 32-bit disk addresses, this strategy implies that every 1024 blocks of the file, 4 MB, were placed in separate groups, the lone exception being the first 48 KB of the file as pointed to by direct pointers. Note that the trend in disk drives is that the transfer rate improves fairly rapidly, as disk manufacturers are good at cramming more bits into the same surface. But the mechanical aspects of drives related to seeks, disk arm speed, and the rate of rotation improve rather slowly. The implication is that over time, mechanical costs become relatively more expensive, and thus, to amortize said costs, you have to transfer more data between seeks. 41.7. A few other things about FFS. FFS introduced a few other innovations too. In particular, the designers were extremely worried about accommodating small files. As it turned out, many files were 2 KB or so in size back then, and using 4 KB blocks, while good for transferring data, was not so good for space efficiency. This internal fragmentation could thus lead to roughly half the disk being wasted for a typical file system. The solution the FFS designers hit upon was simple and solved the problem. They decided to introduce sub-blocks, which were 512-byte little blocks that the file system could allocate to files. Thus, if you created a small file, say 1 KB in size, it would occupy 2 sub-blocks, and thus not waste an entire 4 KB block. As the file grew, the file system will continue allocating 512-byte blocks to it until it acquires a full 4 KB of data. At that point, FFS will find a 4 KB block, copy the sub-blocks into it, and free the sub-blocks for future use. You might observe that this process is inefficient, requiring a lot of extra work for the file system, in particular a lot of extra I/O to perform the copy, and you'd be right again. Thus, FFS generally avoided this pessimal behavior by modifying the libc library. The library would buffer writes and then issue them in 4 KB chunks to the file system, thus avoiding the sub-block specialization entirely in most cases. A second thing that FFS introduced was a disk layout that was optimized for performance. In those times, before SCSI and other more modern device interfaces, disks were much less sophisticated and required the host CPU to control their operation in a more hands-on way. A problem arose in FFS when a file was placed on consecutive sectors of the disk, as on the left in figure 41.3. In particular, the problem arose during sequential reads. FFS would first issue a read to block 0. By the time the read was complete, an FFS issued a read to block 1. It was too late. Block 1 had rotated under the head, and now the read to block 1 would incur a full rotation. FFS solved this problem with a different layout, as you can see on the right in figure 41.3. By skipping over every other block in the example, FFS had us enough time to request the next block before it went past the disk head. In fact, FFS was smart enough to figure out for a particular disk how many blocks it should skip in doing layout in order to avoid the extra rotations. This technique was called parametrization, and FFS would figure out the specific performance parameters of the disk and use those to decide the exact staggered layout scheme. You might be thinking, this scheme isn't so great after all. In fact, you will only get 50% of peak bandwidth with this type of layout because you have to go around each track twice just to read each block once. Fortunately, modern disks are much smarter. They internally read the entire track and buffer it in an internal disk cache, often called the track buffer for this very reason. Then, on subsequent reads to the track, the disk will just return the desired data from its cache. File systems thus no longer have to worry about these incredibly low-level details. Abstraction and higher-level interfaces can be a good thing when designed properly. Some other usability improvements were added as well. FFS was one of the first file systems to allow for long file names, thus enabling more expressive names in the file system instead of the traditional fixed size approach, e.g. 8 characters. Further, a new concept was introduced called the symbolic link. As discussed in a previous chapter, hard links are limited in that they could both not point to directories for fear of introducing loops in the file system hierarchy, and that they can only point to files within the same volume, i.e. the inode number must still be meaningful. Symbolic links allow the user to create an alias to any other file or directory on a system and thus are much more flexible. FFS also introduced an atomic rename operation for renaming files. Usability improvements beyond the basic technology also likely gained FFS a stronger user base. Tip: make the system usable. Probably the most basic lesson from FFS is that not only did it introduce the conceptually good idea of a disk-aware layout, but it also added a number of features that simply made the system more usable. Long file names, symbolic links, and a rename operation that worked atomically and improved the utility of a system. While hard to write a research paper about, imagine trying to read a 14-pager about the symbolic link, hard links to long-lost cousin. Such small features made FFS more useful and thus likely increased its chances for adoption. Making a system usable is often as or more important than its deep technical innovations. Summary 41.8. The introduction of FFS was a watershed moment in file system history, as it made clear that the problem of file management was one of the most interesting issues within an operating system, and showed how one might begin to deal with that most important of devices, the hard disk. Since that time, hundreds of new file systems have developed, but still today, many file systems take cues from FFS, e.g. Linux, ext2, and ext3 are obvious intellectual descendants. Certainly, all modern systems account for the main lesson of FFS. Treat the disk like it's a disk.